In this lecture, we will discuss a very important concept, which is called a quotient groups. So first, what is quotient group? Let G be a sum group. So it is we take it as multiplicative group. Let G be a any group and N is normal subgroup of a group G. Of a group G. So what we have? We have this is a total bigger group, so which is a G, and what is this N? So this N is a normal subgroup of group G. So what is the definition of normal subgroup? It commute with every element of G. So normal subgroup means Ng, which is equal to Gn for every G belongs to capital G. So what is Ng? It is a right coset. So it is a left coset. So in a normal subgroup, there is no distinction between left coset and right coset, because it is a right coset and it is a left coset. So there is no distinction between left and right coset. Now, if I define a sum set G by N, so it is a set of all coset. If I take NA, so for such that A belongs to G. So what is this? It is a set of all right coset of N in G. But since N is a normal, so there is no distinction between left coset and right coset. If I take two element AB belongs to G, so just see that NA into NB, which is equal to NA, and since this is a NB can be written as NA, and this can be written as, so just write in this way. So I take the two right coset, one is Na and second is Nb. So this right coset Na and Nb, this can be written as N into this B, right? Now since N is a normal subgroup, so An is equal to Na. So use this condition at this place. So what we get? We get Na into B. Now here, remember that N is a part of N, as we know that. And we discuss in the property, if HA is equal to H, if and only if this A belongs to H, this property. So by using this property, now since N is a part of N, so it means N into N, which is equal to capital N. So this N into N can be written as a simple N into AB. So this is a property at which NAB can be written as NA into NB. So it means the product of two right coset. So these are the right coset is equal to, that is also a right coset of n in G. Now since AB belongs to G, AB belongs to G, then it implies AB is also member of G. So what we get from this, we get the product of, so what we get, so we get product of two right coset, two right coset is again a right coset. So it again a right coset. So remember that the product of two right coset is again a right coset. Now this set under this binary composition is a group. So we will prove this result, which is our first theorem of this quotient space. So what is the statement? So first write the theorem. So what is the statement of this theorem? Let G be a group and N is a normal normal subgroup of group G. So of group G, G is a group and N is a normal subgroup of group G. So in that case, the set we defined G by N, whose elements are of this kind, NA, such that A belongs to G. So this is a group under binary composition, under binary composition. So what is binary composition? So binary composition. So it is a group under binary composition. NA, NB is equal to NA, NB is equal to NAB for every AB belongs to G. So this element belongs to G and N is normal subgroup of group G. So that I would like to prove the result because it is a group. Now first, what is the element of G by N? So this is NA type. So NA type also can be written as A bar. So what is A bar? A bar is a right coset of N in G. Because N is normal, so right and left coset are same. So also remember the second notation of the member of this G by N set. Now to prove it is a group, what is my first property? So that is a closure property. So I will discuss properly this as a group. So first is closure property. Before that, I prove that this is a non-empty set, because if it is a non-empty set, then we can take any element from that set. So clearly, as E belongs to G, because G is a group, identity belongs to G, and Ne means n, and n is a part of this. So clearly n belongs to G by n. So it implies G by n is a non-empty. So first remember, this set is a non-empty. Why non-empty? Because what is n? N is n into E. And this member is equal to n and it belongs to G by n because E belongs to G. Why E belongs to G? Because G is a group. So that's why G by n is a non-empty. First. Now what is the closure property? So we will take two elements from this set. So I will take either A bar and B bar, या also NA comma NB. So this element belongs to G by N. Then their product, because here the binary composition is multiplication, is also belongs to G by N. So just remember the remember the element of G by N. So its element are n into A type or A belongs to G. So simple. Its member are right coset. So any right coset will belongs to G by N. Now product NA into NB by given binary composition, this NAB belong equal to NAB. So that is a given binary composition. Now this element belongs to G by N. Why? So that is main point. This element belongs to G by N. Why? This belongs to G by N. So why? That is. So it belongs to G by N since A and B, these are element of G and G is a group. Since G is a group, so it is closed under binary composition. So it implies AB belongs to G. So since this element belongs to G, that's why N into element of G belongs to G by N. So this is a closure property. So G by N is closed under this binary composition. So I am not saying multiplication, I am saying this binary composition. Now property number 2, which is the associative property. So for the associative property we need 3 element associativity. So what is the associativity property? So I take the 3 elements. One is NA, NB and third is NC. These are element belongs to G by N. These are element. So what is the associative property? So I start from left hand side. So if I start from left hand side, so this is bracket NA first element, NB second element and bracket into NC, this values. Now by using the binary composition here, so this can be written as NAB into NC. Again I am using the binary composition, so this can be written as N bracket AB into C, this values. Now what is the element of ABC? Element of ABC belongs to G. So since A, B and C, these are element belongs to G and G is a group, and if G is a group, so they satisfy associative property. So what is associative property? AB into C, which is equal to A into BC, this value. Now using this concept here, what we get? We get N here. This is shifted as A into BC. Now it means BC is treated as one element. A is treated as one element. Now apply binary composition. So this is can be written as Na into NBC, this values. Now this is treated as single element. It is treated as single element. So this can be written as Na. Now this single element treated as NB into NC. So what we get? We get NA into NC is equal to this kind. So it means NA NB into NC, which is equal to NA into NB into NC. So what is this? This is the associative property. This also written as A bar B bar, which is into C bar, which is equal to A bar into B bar into C bar. For every A bar, B bar and C bar, it belongs to G by N. So this is a second property, which is a associative property. Now what is the third property? Which is existence of identity. So what is the third property? Which is existence of identity. Existence of identity. So what is the existence of identity? So which satisfy the condition, which is N into NA. Now here identity is N. Why? So just see that since for G identity is E belongs to G. So what is NE? N is N. So this is a identity. This element is identity of G. So check that for every NA, for every NA belongs to G by N. So there exists N, which is basically NE belongs to G by N, such that it satisfies the property of identity when we multiply this N into NE, this N into NA. What is its value? So this value is NE NA, which is N into EA. So what is this? This is a NA. So when we multiply on the left hand side, so it will converted to itself. What is identity? That converted the element to itself. Now in the NA into N, so in the same line of action, NA into NE. So this is a N into AE. So what is this? This is a NA. So what we get? We get N into NE, which is equal to N, which is equal to NA into N, which is equal to N. Similarly, NA into N, this values. So here remember that identity is capital N. So remember here identity is not E. Here identity is capital N. So identity of G by N is a N. Now after that the property fourth, which is existence of inverse. So what is the property number 4? So this is a existence of inverse. Existence of inverse. So what is the existence of inverse? So for every NA belongs to G by N, there exists a element NA inverse belongs to G by N, such that this NA into NA inverse can be written as N into A into A inverse. Since A is a member of G, so A into A inverse is identity. So this is equal to N. So what is N? N is identity of G by N. Similarly, NA inverse into NA, which is equal to NA inverse into A. So this is again identity. So this is again equal to N. So what we get? We get NA into NA inverse, which is equal to identity, and this is NA inverse into NA. So what it means? It means inverse of any vector NA, inverse of any vector NA can be written as of this kind NA inverse. So this is a existence of inverse. So it satisfy all the properties of group, then G by N is called a group, and this group is called a quotient group. So remember that. So this is called a quotient group. So which is a quotient group, and here it is a quotient group under multiplication. So if the binary composition is addition, if binary composition is addition, then G by N is of this type, because in additive the right coset is N plus A, such that A belongs to G. So this is a binary. G by N is under addition binary composition. So what is its binary composition in addition? So that is N plus A plus N plus B. So this can be written as N plus A plus B. So first thing to remember. And second, what is the identity of G by N? So identity is N plus 0, which is N. So what is inverse of N plus A? So inverse is N plus A. The inverse of N plus A is N plus minus A. So remember that its inverse is this and its inverse is this. So what is identity? Identity under addition is simply N. So N plus 0 is again N. So this is the identity of this. So this is called a quotient group.